Alright, my dear children of class 12 science, so we will be solving now few important numericals from this chapter, atom and origin of spectra. And then this numerical problem which I will be solving has asked already in IRC also and still important for your coming examination. Okay, so let's start with problem number 1. Problem number 1 said that is a question came in IRC 2016 and 2018, important numerical, and this is a problem based on the emission of radiation in case of hydrogen atom or hydrogen spectrum. Okay, and question say that calculate the minimum wavelength. Now see, minimum wavelength is also called short wavelength, also called what? Short wavelength or shortest wavelength, okay, of the spectral line present in Balmer series of hydrogen. So you have to calculate the shortest wavelength or minimum wavelength, okay, of the spectral line present in the what series? Balmer series of hydrogen spectrum. So in order to solve this problem, we know the different series of hydrogen spectrum in case of emission radiation. Now for Balmer series, now this problem is basically with what series? Balmer series. And when we talk about Balmer series, the emission of radiation and to calculate the wavelength of emitted radiation can be measured by this formula. 1 by lambda equals to R with 1 by 2 square minus 1 by n square, where n starting from 3, 4, 5, these are the higher orbits. It can be infinite also. Okay. Now from this relation, we have to find the minimum wavelength. Now when we get minimum wavelength or shortest wavelength, when electron jump from what? Infinite orbit to the second orbit. Because in Balmer series, the lowest orbit is what? The lower orbit is always what? 2. And the higher orbits are 3, 4, 5 like that. Okay. Now in order to get the minimum wavelength, so I write down this is for minimum, also called short wavelength. Let me use the word shortest wavelength also. Minimum of what wavelength? Shortest wavelength. The electron has to jump from from infinite orbit to the second orbit. Means when electron jump from infinite orbit to the second orbit, then we always get the minimum of shortest wavelength in Balmer series. That means n must be equals to what? Infinite. Because your lower orbit is already 2, that means when I put n equals to infinite, and when electron jump from infinite orbit to second orbit, the wavelength which we measure is the shortest or minimum wavelength. Okay, so for that let me just do the calculation. 1 by lambda equals to R. And children, you know what is R out there? It is called Rydberg constant. Bracket 1 by 2 square minus 1 by what? Infinite with whole square. And children, you know that 1 by infinite square means infinite only, and 1 by infinity is always 0. This coded is 0. So 1 by lambda equals to R into 1 by 2 square is how much? 4. So 1 by lambda equals to R by 4. But actually we need to find lambda. So just reciprocal, lambda equals to 4 by what? R. So with this relation we measure the wavelength. Now for that, let me just substitute the value 4 by, now R value is 1.097 into 10 to the power 7. Okay, now let me take the power in the numerator. Now 4 I will divide by 1.097. If you divide 4 by 1.097, we get 3.646. Approximately we get, you can use the calculator, divide this quantity, we get approximately 3.646 into 10 to the power. Now this 10 to the power 7, if I take in the numerator, minus 7. Now this is basically, we measure in meter. But as I said, when we measure the wavelength and when it is asked to measure the wavelength, we measure and keep the unit in Armstrong. Means we change meter into Armstrong. So how to convert meter into Armstrong? And you know 1 Armstrong is equals to 10 to the minus 10 meter. So I have to make this power minus 7 as 10 to minus 10. Okay. So what you need to do? So look at this. Negative power, there is a decimal. So by how much negative power I have to increase to make minus 10? Minus 3. So if I increase the negative power by 3, this decimal shifted by 3 decimal. So if I shift this decimal to 3 decimal right, then your power increases by minus 3. Okay, so when there is a negative power, children, look at this part again. When you shift the decimal 3 decimal right, your power increases by 3, which means we write down 3646 into 10 power minus 10, because it is already 10 minus 7. If the power increases by minus 3 means minus 10. Now 10 to minus 10 meter means nothing but 1 Armstrong. Now finally the answer is lambda equals to 3646 Armstrong. So look at the value. This is the minimum or the shortest wavelength, okay, that can be measured under Balmer series of hydrogen spectrum. And you know, Balmer series of hydrogen spectrum basically lies in which region? Visible region, visible light. Okay, so this is one of the numerical based on Balmer series. Now we will be solving our next numerical, that is problem number 2. Now the problem number 2 says that in a hydrogen atom, a transition takes place from n equals to 3 to n equals to 2 orbit. Now see, for hydrogen atom, this is the solution I am doing for this atom, hydrogen atom. Okay, now for hydrogen atom, what transition takes place? From 3 to 2. 3 to 2 means the electron jumping from orbit number 3 to orbit number 2. So when electron jump from 3 to electron jump to 2 orbit means basically we observe this hydrogen spectrum of hydrogen series in what? Balmer series. Basically what series? Balmer series. We have done it already. Now for this particular question, what actually you need to find out? Calculate the wavelength of emitted photon. So when electron jump from orbit 3 to orbit 2, the emission of radiation takes place, or emission of photon takes place, and that emission of photon has a particular wavelength, and that wavelength we need to calculate. So wavelength that we need to calculate. So in order to calculate the wavelength, okay, when electrons jump from any of the higher orbit to any of the lower orbit, then the formula is 1 by lambda equals to r 1 by n1 square minus 1 by n2 square. See, we know this formula, so we have done it already. 1 by lambda equals to r bracket 1 by n1 square minus 1 by n2 square. So out here, if you see, n1 equals to 2. This is for lower orbit. That means electron jump from higher orbit 3 to higher orbit, lower orbit 2. That means n1 is the lower orbit, that is 2, and n2 is the higher orbit, which is what? 3. So n varies as n2 in the higher orbit, and n varies as n1 in the which orbit? Lower orbit. Okay, so when electrons jump from 3 to 2, definitely we can measure the wavelength, and that wavelength can be calculated by this relation. So let me just calculate 1 by lambda equals to r with 1 by n1 I write on 2 with whole square minus 1 by n2 I write on 3 with whole square. R 1 by 2 square means 4 minus 3 square is what? 9. Okay, now 4 and 9 LCM I'll take. 4 9s are 36, so LCM is 36. So 4 divided to 36 is 9, 9 1s are 9. Minus 9 divided to 36 is 4, 4 1s are 4. So that's why it is 4 minus 9 minus 5, 4 is how much? It's simply what? 5. So it will be 5r by what? 36. So children, look at this. 1 by lambda is 5r by 36. Means we can just reciprocal lambda equals to 36 by what? 5r. So from this relation we can measure the wavelength. Now for that, let me just again do the calculation. 36 by 5. Now see, value of r already given in the question. That is 1.097 10 power 7 per meter. 1.097 in 10 power 7 per meter. Okay. Now with this calculation we get the value up to certain range. Now let me take this power in the numerator. So 36 by 5 into 1.097 into 10 power minus 7. So look at this. So lambda equals to 36 by 5 into 1.097, and the power which I have taken is 10 minus 7. Now this denominator part can be calculated, multiply. When we multiply this quantity and divide to this 36, we get approximately 6.563. So children, you can even do the calculation by yourself. Multiply this quantity and divide to 36 means you get approximately 6.563 into 10 to the power minus 7 meter. But children, I have already said that you have to write the wavelength in what? You have to write the wavelength in Armstrong, and this wavelength which we are measuring is in meter. So I have to convert this meter into Armstrong. So I'll make this power minus 7 as minus 10. So what you need to do, when there is negative power, shift 3 decimal right. If you shift 3 decimal right, okay, then your power increases by 3. So minus 7 become minus 10. Because minus 7 minus 3 means minus 10. Okay, now see, this 10 minus 10 meter means nothing but 1 Armstrong. So final answer is lambda equals to 6563 Armstrong. So look at the value that we calculated. The value that we calculated is 6563 Armstrong. So this is the wavelength of emitted photon, okay, in hydrogen atom. Now after that, the question says that, will the photon be visible? Yes, the photon will be visible. You know why? This wavelength lies in visible spectrum. This wavelength which we have calculated lies in the range of visible spectrum. Now because the range of visible spectrum is how much? 4000 Armstrong to what? 8000 Armstrong. So this is the wavelength range of which spectrum? Visible spectrum. Visible spectrum. So you can see now, this wavelength also we calculated, lies in this range only. That's why this particular photon will be what? Visible. Okay. Now after that question say that, to which spectral series will this photon belongs? Yes, and this series is nothing but Balmer series. See, you have already learned in detail about the different series of hydrogen spectrum, and this wavelength lies in which series? Balmer series. Because Balmer series of hydrogen spectrum always lies in visible region or visible spectrum. Okay, so this is also one of the numerical that we have done based on Balmer series. This is a problem based on Balmer series. But let me just tell you children that this wavelength that we calculated when electrons jump from 3 to 2 is actually the longest wavelength. This is the longest wavelength. And problem number 1 which we did, it was with shortest wavelength or minimum wavelength. But this is for what? Longest wavelength. So there are other numericals to solve that we do in the next YouTube video.